Well, what happens when we make a solution between a solid and water? We take a solid and dissolve it in water. There's a bunch of different interactions going on. Here's our water molecules, and there are forces of attraction between the water molecules. Those are the solvent-solvent attractions. And here's our sodium chloride that we're dissolving in the water. There's an ionic bond that is a form of attraction between the sodium ions and the chloride ions. But then there's also an attraction between the sodium ion and the negative end of the water molecule, and there's an attraction between the chloride and the positive end of the water molecule. And this is why water can dissolve an ionic compound, because it is also polar. And so these forms of attraction here, these intermolecular forces of attraction, are a little bit like a language. And so these two molecules, or the molecule and the ion, have to be able to speak the same language to be attracted to each other. If the solute-solute attraction and or the solvent-solvent attraction are too strong, the substance will not dissolve in water. So it's a balance between the attraction of the substances for themselves and for each other. So calcium carbonate is an ionic compound, but it doesn't dissolve in water. And that's because the attraction between calcium ion and carbonate ion is stronger than its attraction for the water molecules. And so it's not going to dissolve. It's going to stay together. So here's an illustration of a sodium chloride crystal. We've got the sodium ions and the chloride ions. And the little water molecules are curious, and they're swimming up here. Water swims because it's in water, right? The water molecules swim up here, and the positive ends of the water molecules are attracted to the negatively charged chloride ion. And they come over and say, hey, come on out and play with us. He's like, well, no, but I really like these charges. I'm really attracted to these charges of the sodium ions. Oh, well, we've got charges too. And so they get around the chloride ion, and they replace the charge that the sodium was giving in attracting this. They replace it. It takes multiple water molecules to replace the attraction of the one sodium ion. And then over here, sodium is having the same experience, except the water molecules are turning the negative end towards the sodium ion. And so in this way, the water can replace that electrostatic attraction between the positive and negative ions and allow these ions to move about in solution. As this dissolves, these are going to move around and they'll become uniformly distributed and create a solution. We're not going to have a localized concentration of sodium ions or chloride ions. Does that make any sense? In order for something to dissolve in the solvent, there has to be forces of attraction between the solvent and that solute. So when we add salt to water, now obviously that giant block of sodium chloride isn't going to fit in that beaker, but it's an illustration, right? When we add this crystal of salt to the water and the ions dissolve, now they are mobile. They can move around and they get dispersed and spread out. The sodium chloride does not just sit at the bottom. It appears that it disappears, right? If you put salt into water at home and you stir it, it looks like the salt is disappearing. Where does it go? It's dissolving in the water. It's mixing with the water. If you try to do the same thing with sand, it's not going to work. Or pepper or flour. It will not disappear into the water. The particles will remain and eventually they'll settle to the bottom. That's not a solution. The idea of solubility is a quantifying of how much of a compound will dissolve in a particular amount of liquid. If you keep adding salt to a glass of water and you keep stirring, eventually you'll come to the point where no more will dissolve. And we say that that solution is saturated. It's full. like a sponge, may be saturated with water, and you could pour a little more water on it, but some will leak out. It won't hold it anymore. We get flash flooding when the ground is saturated with water, and it rains, and the water just runs off because it doesn't have anywhere to go. It can't soak into the ground. So one way to define solubility is to give a mass of that compound that will dissolve in 100 grams of water. So for sodium chloride, and the solubility is somewhat dependent on temperature, so we usually specify that. 36 grams of sodium chloride will dissolve in 100 grams of water. That's a lot of salt. You can add a lot of salt to water. At that point, the solution is saturated, and if you add more, it is not going to dissolve. It'll just fall to the bottom and sit there. So when we say we have a saturated solution, it's full. Unsaturated just means that we have less solute than the maximum amount. If you add more solute, it will dissolve. Adding more solute to an unsaturated solution, it will dissolve. And then there's the supersaturated solution. The supersaturated solution has more solute than can dissolve at that temperature. Does that seem impossible? You have to elevate the temperature to create a supersaturated solution, and you cannot create a supersaturated solution out of every solute-solvent combination. One way you can do this is with pressure, another is with temperature. Sodium acetate makes a very nice supersaturated solution. You heat up the solution to get all the sodium acetate to dissolve, and then you just let it sit there and let it cool down without disturbing it. It's like you're sneaking up on it. And so it's cooling down, and as the temperature goes down, the solubility of the salt goes down, but it's like it's clueless. It's like the Roadrunner or Bugs Bunny, and they run off the cliff, right? And they're fine until they notice that they're in midair, and then they fall. So the supersaturated solution has run off the cliff, and it's not until you bump it or throw a crystal into it or disturb it in some way that it realizes, oh wait, I can't have this much solute dissolved in me. And then it will all come out of solution. Another way you can do that is with pressure. So the sudden release of pressure causes the carbon dioxide in a soda to come out of solution. Carbon dioxide is not very soluble in water under normal pressure. But if you increase the pressure, you can get a lot of carbon dioxide to dissolve in the water. Then when you release that pressure, the carbon dioxide starts to come out. And that's why if you look at a clear soda bottle, like a 2-liter bottle, and you look at it, you don't see any little bubbles coming up. It looks like there's maybe even no carbonation in there at all. But as soon as you open the lid, what happens? You start to see bubbles coming up. And that's because it was a supersaturated solution. When you release the pressure, it starts to come out. Here's a series of pictures showing a supersaturated solution. So this is this was created by heating it and allowing it to cool slowly. And it will sit there like that until it gets disturbed. And so what they're doing here is they've got a little tiny crystal that they're dropping in here. And when that happens, it starts to crystallize all over the place until it's almost solid with crystals. We've talked about the solubility rules, how these sorts of compounds are generally soluble and these are generally insoluble, and the exceptions. Do you remember those guys? There was a table of solubility rules. Those give us qualitative descriptions. They say what will dissolve in water. But they don't give us really a quantitative description. Some of those ones that are insoluble because the attraction between the ions is greater than the attraction between the solvent molecules and the solute. You can also have molecular solids that are soluble in water. Table sugar is a polar molecule, and it also dissolves quite well in water. Nonpolar solids, such as lard and vegetable shortening, bacon fat, generally insoluble in water, because the types of intermolecular forces they have are very different. So if we have something that we dissolve in water and it produces ions, these are called electrolyte solutions. They have charged particles dissolved in the water, and they will conduct electricity. And when they talk about, replenishing your electrolytes after exercising, they're talking about the same sort of thing. They're saying you need more salt, not just sodium chloride, but you need magnesium and potassium and different ions to replace the ones that you lost when you were sweating. A non-electrolyte solution does not have charged particles. So something like a sugar solution, it's a solution. There are particles dissolved here, but they do not have a charge. And so this solution cannot conduct electricity. An electrolyte conducts electricity. A non-electrolyte does not. The solubility of solids generally increases with increasing temperature. And so here we have a graph. There's temperature on the x-axis and solubility in grams per 100 grams of water on the y-axis. If we look at sodium chloride, it's this almost horizontal black line in the middle. The solubility of sodium chloride in water does not change much with temperature, but some of these change a great deal. Here's potassium nitrate. At room temperature, about 25 degrees, it's about 35 grams per 100 grams. At 50 degrees, it's close to 90. It changes a great deal. Most of them go up in solubility. There are a couple that become less soluble, but generally solids will increase in solubility as the temperature increases. One way that a solid can be purified is through recrystallization. And so you take the solid that you're trying to purify and you dissolve it in water. And you make a saturated solution at a higher temperature. You'll get more dissolved at the higher temperature. And then you let it cool down slowly. And as it cools, the solubility decreases and causes some of that solid to precipitate out. But it's doing that slowly, and so the crystals become more perfect as they crystallize slowly, because when they line up perfectly, then the forces of attraction are maximized, and so they will tend to reject impurities as the crystals are forming, and so you can get rid of impurities that way. You guys ever had rock candy? I remember trying to make this as a kid, but I didn't know what I was doing, and so it didn't work. But rock candy is formed through recrystallization. You make a saturated table sugar solution. So you take just regular table sugar, and you heat it, and you make a saturated solution. And then you put a string in the solution, and you let it cool. And the crystals of sugar will form on the string. And you get these nice big crystals of sugar.